Good evening, everyone. My name is Harsha. I'm the co-founder and CTO at Interface. We are a research lab that is reinventing transformers. Today, I want to talk about how we managed to build a new architecture for deterministic developer tasks. Now, it is no mystery that in the past 2 decades, AI has gone from being a rigid machine learning model to a larger scale generalizable intelligence, which you can use today for AI workflows. We've gone from building structured fine-tuned models to today prompting that allows you to build agents. More specifically, think about this. Early 2010s to 2015s, you're a bank. You want to do OCR. How would you go about it? You would have to purchase or procure large data sets. Not only that, get a talented team to build that model, deploy, and then maintain it. This could easily cost you about a few hundred to even millions of dollars. Thanks to invention of large language models, we are able to do that with prompts. However, there's still a problem of hallucination. Though models like GPT are now massively multimodal, and we are seeing it with Gemini, they still hallucinate. This happens because of context drift. When you want it to behave deterministically for large inputs of data, you see hallucinations happen. We at Interface are solving this exact problem by designing a new architecture that we train. So we bring the rigidity of a machine learning model and the flexibility of a large language model. So how do we go about this? You use machine learning models as strong encoders for very specific tasks. And then you use large language models to create the decoding phase of it. Today, I want to showcase a few things as to what this model can do. I want to quickly showcase 3 things. I'm going to talk about it. I'm just going to quickly run it so that we have time to talk about it. So first thing, this is a real document. I want to extract data from it. Not only the text, but I also want to detect the faces on it, and also calculate its age to verify it. So we ran Interface for this. This is what Interface gave us. Not only did it extract the text, it gave you the bounding boxes of where it saw the text in the image, the actual pixel coordinates. It got both the faces right, and more importantly, it managed to calculate the age correctly. That's right. Now let me show you one of the specific model providers or OCR providers that also does OCR. That is Reducto. A lot of you might have heard about it. Reducto did extract the text correctly, but it failed to do the other parts of it. Detect where the text is and calculate the age. Now this happens because of a stronger encoder. Let's go to the next one. We want to scrape this particular LinkedIn page. Surprised that Gary doesn't follow me yet, but okay. So we want to extract Gary's experience. LinkedIn can be a pain to scrape because of the blockers and bot checks they have. I want to extract his experience beyond this button. Now that's going to be interesting. So let's see what Interface did. Not only did it give us what it saw on the first page, but it goes all the way back to his internship. We are able to do this because of our own model, which is able to scrape LinkedIn. And lastly, I want to go about a PDF, a dense PDF. Sorry. So I just have to run this again. So on this screen, you're seeing a dense PDF that is supposedly a research paper for this particular model. We want to extract this entire text and translate it to Hindi, and also count the number of characters in this PDF. As it runs, I want to go back to the presentation because that's going to take time, and then talk about it. So now that we saw the demo as to Interface can do, I want to talk about how we managed to do it. I want to talk about what we actually trained. How did we do OCR? Before that, I want to showcase where we stand as well. On your screen, this is OLM OCR bench, which tells you how good a model is at handling complex documents, not only from research papers, but also complex handwriting for massively multilingual OCR. We are number 1. When compared to even specialized models like Chandra OCR, or even specific providers like Reducto. This is the example that you saw, and this is the output that you saw. What is happening under the hood is that this image is fed as input to the encoder that we trained, which is a CNN stack, that tells you the text regions. Each of these text regions becomes the becomes the location of crop. So you crop the image from where the text is, use that to give it to the decoder to generate the output. Now this gives you confidence scores, this gives you bounding boxes, and metadata that you can actually trust beyond just simple text. We can go a step forward and feed that information to a larger model, which is a decoder that we also have conditioned upon to extract structured output. That's where the age aspect came from. You get the information, and then you condition on top of it. That is OCR. Now I want to go to object detection. How did we manage to detect faces? Now that is object detection with natural language. YOLO models are great, but they only detect specific objects that they are trained for. We are number one for natural language object detection, meaning you pass in a prompt. Let's take this room. I give a picture of what I'm seeing in front of me, and I say, detect everybody who's wearing a black t-shirt. Interface would be able to do this. That's a complicated thing to do. How are we able to do that? So you take the same image, you have a text encoder, which is encoding the text aspect, understanding what the user wants. You have an image encoder, which is understanding or representing the image in positional aspects, and then creating a contrastive segmentation, meaning it is pulling pixels which are closer to each other, allowing you to detect the objects accurately. If you use that information a step further, you can now segment those pixels. Same thing, image encoder, prompt encoder, and then you have a mask decoder that will classify all pixels to give you a latent mask. ASR, multimodality is a huge thing. Not a lot of models support speech out of the box, and I want to talk about it today. We are one of the fastest models when it comes to ASR, and we also have the lowest VER, word error rate. So how do we do it? So when you give a long form audio, we first detect wherever the speech is happening, and then crop those audio clips. So we get the chunks. And then use those chunks to extract acoustic features for an encoder which is also trained to extract embeddings for speech features. Now these embeddings are used to cluster. Clustering allows us to segment features into groups. And that gives us diarization output. So now you know which audio is by which speaker. But the text comes from the encoding part again, where you convert the audio into a spectrogram. A spectrogram is basically a visual representation of audio. And then you use that as a frame to generate or classify text. So whatever the pronunciation is, that would particularly be classified into text. So before going to the next thing, let's see what interface gave for translation. So for this, you can see that interface not only managed to extract all the text and translate it to Hindi, but it also stayed relevant and safe where it's not supposed to. Like, it did not translate addresses, it did not translate author names, and it also correctly calculated the number of characters. Now, we put this against Claude 4.7 Opus to see what Claude would do. We gave it 3 tries, and that's why I went back to this. Claude failed all 3 times. It did because of a timeout. But even if it were able to, and if it is a long horizon task, there's a problem with multilinguality, especially with South Asian languages. Let's go back. So we saw 3 things: vision, audio, and text. While working with these 3 encoders, we trained these adapters to work with the same decoder. So you would get accurate data, but you know where that data is being extracted from. You could solve multimodality this way. Today, I'm super excited to showcase our numbers as to 3 modalities that I was just talking about. We compared interface to models that you would traditionally use in production, and these models are economical and can do the tasks in one shot. But we are comparing them for deterministic tasks. Tasks where there is only one output. If you're looking at an image, my name cannot magically change. It's going to be still Harsha. Johan and I and my team have been researching about how do we build task-specific models for about a year now. We did the same things. We picked small language models, we procured large data sets for a lot of money, and we kept running into the same problem of determinism. Models hallucinate. That's where we thought we have to go back to the board, redesign the architecture, and rethink it. We observed that data is not the bottleneck, the architecture is, and that is what interface is supposed to solve. Lastly, it's been such a pleasure to speak in such an amazing audience and such a beautiful country. Thank you.
Interface!